So today we'll start off with a new topic in the context of physical chemistry, and that topic would be quantum mechanics. This is a much anticipated topic among students. So, what is basically quantum mechanics? It is basically the dynamics for small subatomic particles, wherein we find that the Newtonian mechanics has failed to give us proper results and to understand the physics behind their, and the main aim will be to understand the physics behind their behavior in the subatomic realm. So, and this topic is actually very intuitively difficult to follow, and however this is not a very difficult topic to follow mathematically, and we shall try our best to follow it mathematically, even if we cannot follow it intuitively. So I would like to tell you that there are certain prerequisites to understanding quantum mechanics, and we call those prerequisites as formalism. And the first topic that we should know when we are starting off with quantum mechanics is the idea of operators. Now we know what are operators, right? So what is new about us study now about operators? We know that there are actually two types of operators. One are the unary operators. One class is the unary operator, and the other class is binary operator. We are just going back to our basics, and before we go off to the unary operators, which will be more important, we shall remember that the binary operators, that we are more actually familiar with the binary operators, which are plus, minus, multiplication, division, and the list may go on, and you can think about multiple maybe made up binary operators. Maybe there are several unary operators as well. Can you name a few unary operators? Actually, there are the most famous unary operator if you think about it, is the famous derivative operator. In fact, the difference, and now you must have realized the difference between the unary and binary operator. So the unary operators are those operators which actually act on something and give us a certain result. So, and the number of things that are required by the unary operator to act on is actually 1. So remember that derivative operator, how many functions do you need? What is the minimum number of functions that a derivative operator can act on at a time? It is actually 1. So 1 function, right? While on the other hand, binary operators, if you remember, that they require at least two functions or functions or numbers to act on, while the derivative operator requires only 1. We have the integral operator, which also requires only one function to run, and then we have the log, exponential, all those things. These are functions mainly, but yeah, we can count them as operators as well. We have the square root operator as well. Anyway, so the thing that is most important is operators are instructions which basically act upon a function to give us some result, right? And in the context of this quantum mechanics, what becomes more important is our unary operators, and what becomes even more important are unary operators, and within unary operators what becomes even more important is something which is, it's a derivative operator. and this is something we should be keeping in our minds. There is another type of unary operator which is a scalar multiplicative type of operator, which is say x. Okay, so x is basically an operator. So whenever x, let's say x is an operator which is a scalar operator which is acting on, let's say, a function f, right? Actually this operator is actually acting on f to give you a new function which is actually xf, and this x, to distinguish that this x is an operator, we write a hat on top of this x, right? So to distinguish between a function, to distinguish between operators, whether something is an operator or a function, we actually put, let's say we have an operator, let's name the operator a, call it a, and we put a hat over this. So this is the notation for operators, right? Secondly, you must be realizing this, and it needs no saying, that operators do not have any meaning without a function. No function, what will the operator act on? Nothing. So no result. So what is the meaning of the operator, right? And let's talk about now order of operation on a function. Order of operation. Let's say we have two operators a and b. Is it right to say, we don't know what these operators are obviously, is it right to say that a, and let's say they act on a function f, is it right to say that a acting on, let's say we first operate f with b, right, and then we decide to operate this new function, what, let's say what is the result, let's say let's call this a function g, because obviously when the operator b will act on f, it will generate a new function g. Okay, let's call it g. Now ag, when a will act on g, what is the result? Let's call it h. Okay, and let's say a acts on f, what will be the result? Let's call it g1, and then b will act on g1, let's call it h1. Now my question is it right to assume h is equal to h1? I pose this question to you, and if you notice, what I have just done is change the order of operation from first b to a and then a to b. This is actually written in terms of operator algebra. This is operator algebra as ab on f. So first a acts on bf, right? Is it equal to a b acting on af? Is it right to say this? And this is actually written this way, that ab, this is often written as this way, this is just the notation. So whatever is inside acts first on f. Okay, so actually this is often not right to say. Actually this is not a right statement. This is not correct always. And there are several reasons, and this actually has some significance why this is not correct always, and we shall see actually by taking some examples. But if indeed this is true, but if indeed this is true, A and B are said to be commutative, and here I will define the first operator that we know of. The first operator that we will define here is something called as the commutator. What is this commutator? It is actually written AB in square brackets. Okay, and this is actually defined as AB F minus DAF, and in notations we often write this as AB minus BAF. But don't forget that we must always remind ourselves that this is not multiplicative, rather we have this is just a notation. So first we have to operate AB on F and BA on F, like the process said before. AB on F and then BA on F, and then take the difference, right? This is nothing but the notation. So commutator is this. Now if indeed A and B commute, right, if indeed A and B commute, then this commutator operator AB is equal to 0, and this means that sequence in which A and B operate on F, sequence of A and B operating on function F is unimportant, right? Now we shall understand that understand this with the help of an example, right? Can you determine this commutator? Okay, wherein we have the A operator. If you compare with our definitions, we have A operator written as x and B operator written as ddx. Okay, and obviously this is a case in which there is only one function, one changing variable, which is x, which, and thus this is an example of homogeneous functionality. Anyway, let's forget about it. So how do we check whether x and ddx commute? Let us assume a function f. Easiest way to do, assume a function f, fx, right? So we have x. So if we go by our definitions just as before, we have x ddx minus ddx on x f. This is just by this rule, just using this rule. And if we have, let us remove the hats to remove the confusion, ddx, and we take this in f here, and we have ddx on xf. Okay, the first term, nothing much to do here, right? And this is actually, I remember telling you about that this x is a scalar multiplier operator, and the second term is a UV rule, product rule of differentiation. So we have x df dx plus f dx upon dx, ddx on x is 1, so not writing doesn't make sense here. So f df dx minus x df dx minus f. Now these terms will cancel off and we have minus f. That is very weird, and we have x d dx on f, and f is actually turning out to be minus f. So clearly we have so clearly f was something non-zero function, can be a non-zero function, and this is obviously not equal to 0 unless we took f equal to 0 by some weird miracle. So no, unless f is not 0, the commutator will also be not 0, and hence if it is not 0, x and dtx operator never commute. Okay, actually there is a notation that we must be aware of, that whenever that x d dx is on f is actually equal to minus f, we can actually notation wise we can actually remove the f's and actually write this as if we have cancelled out the f, that we can write this as minus 1. It seems like we have cancelled out the f's, but this is just a notation. Just remember that this is a notation, and this symbolizes that whatever be the function, if we operate with the commutator operator, the result will be the same function with a negative sign. And this is actually an important concept of quantum mechanics, which we will discuss in the future videos, in a future video, right? Now if there be functions which are commutative, which are non-commutative, there must also be functions which are commutative. Indeed, there are functions which are non-commutative, right? So consider this operator, this commutator, wherein we have the two partial derivative operators with respect to f del x and del y, which will be acting on fxy. Let's see, right? So partial derivative operator will act on fxy, and we, let's say xy can be written with actually variable separately. Let's not worry about that for a moment, and let's say that this is actually nothing but f1x into f1y. Okay, so x and y parts are independent of each other, right? For now, let us not bother. Let's just look at the mathematical point of view, from a mathematical point of view. So we have del x operator and del y operator acting on fxy. Now this del x operator, okay, let's write it down first. Del x acting on del y del y on f1x times f1y minus del y del x on, so directly writing on f1x times f1y. Okay, now this y operator, this y differential will act on the f5 part only. Okay, and actually it will act like this, that del x on f1y on f1x, this f1x will act as a constant and come out of the differentiation, del y f1y, so it comes out, and we have here del, and in same case the fx remains when the fy comes out. So we have del y f1y into del x f1x, right? And if you notice that these two terms are one and the same thing, because they are just separated by a product, right? They're separated by a product, and we know product is itself commutative. We can change the order of product, and this is actually equal to 0. Thus these two indeed commute. The partial derivative operators with respect to x and y indeed commute with each other. Next is, I would like to determine another commutator which is actually very important in the context of quantum mechanics, is this. Rather better to write del f del y and write fxy, where fxy is actually equal to, let's say, gx hy. If you calculate this, which I think you should be able to do right now, it will be, well, I'll try for you. So this is fxy, this is gx hy minus del y x gx hy. So this is x, and we have gx here, so gx comes out, and we have del y on hy minus, so we have only y dependence, so this is x gx into del y hy. And this entire thing cancels off to be 0. Thus these two operators x and del y also commute. Okay. Next important thing that we should understand is something referred to as linearity of operators. Okay. So in quantum mechanics, actually the idea is very simple, that the operators must be linear, and that is why, remember, I was telling you in the beginning of the lecture that that derivative operator should be very important. The reason is, well, derivative operator is a linear operator which actually appears very frequently in quantum mechanics. And not only derivative, in fact all the derivatives which actually happen, there's a second order, or let's say nth order derivatives, they are all linear operators. And linear operators, so let's write down that derivatives are linear operators, and these linear operators called derivatives, or derivatives rather, actually occur in quantum mechanics a lot, and these are generally the first and the second order derivatives. Okay. So by the what do you mean by linearity of operators, which we might be asked to check, which is an important question. Okay. Two simultaneously important criteria must be satisfied by two operators, by an operator A to be important in quantum mechanical context. So if A, let's say, acts on two functions f and g, okay, acts on a linear combination of functions f and g, the result is actually AF plus AG. And second important criteria is A acting on CF is actually C is the same as C. C will come out when C acts on AF. So this is actually this is how we will verify whether an operator is linear or not. And to check whether an operator is linear, we'll have to check both sides of the equation. Let's say we define an operator AF to be 1 by f. Can you check whether this is linear? Can you check linearity? Linearity is can we check? It's a fairly simple exercise. Firstly, let's take two functions f and g. So can you tell me what will be A operating on f plus g? So A operating on any function f is 1 by f. So A operating on this function f plus g is 1 by f plus g. And well, if you see carefully, this is not equal to, if it had to be linear, it should have been equal to, well, this was this. Let's check the right hand side. Then what is AF is 1 by f and AG is 1 by g. Now A on f plus g is not equal to A acting on f plus A acting on g, right? Because the reason is 1 by f plus 1 by g is not equal to 1 by f plus g, right? Check the second criteria. Even though we are sure now that this is not linear, check the second criteria. CAF, rather ACF was actually 1 upon CF, and CAF was actually 1 upon C upon F. Clearly C upon F is not equal to 1 by CF, and thus A is not linear. Now check the second operator, which is A equal to AF equal to F star. I will leave this as an exercise, and we shall discuss the solution in the next class. Thank you.